Hello dear students, welcome back to the lecture series on theory of semigroups. Today in this lecture we will discuss semigroup presentation, or you can say presentation of a semigroup. Okay, so we already defined three semigroup. Now suppose we have a given semigroup and it has also a generator. See, like we have a semigroup n with plus operation, and one is its generator, because 2 is equal to 1 plus 1, 3 is equal to 1 plus 1 plus 1, so 1 is its generator. So let's assume that let S be any semigroup, let S be a semigroup, let S be a semigroup, let S be a semigroup. Let S be a semigroup and A be its generator in this sense, and A be its generator. It may contain more than one element. So in case it's a singleton set, then it's called a monogenic semigroup. So then this A is subset of S here. Now let's if we define I, let then I, the inclusion map, then the inclusion map, then the inclusion map I from A to S. Then we have an inclusion map. We have the inclusion map I from A to S. So by definition of pre-semigroup, what's the definition of pre-semigroup actually? The definition of pre-semigroup is that given a set of letters, we can construct a free semigroup A plus. We can construct semigroup A plus such that we can define a map from A to A plus. Okay. And for any other map from A to any other semigroup S, then we can define a map. Then there is a map from A plus to S. So this is an embedding alpha, and there is S is any other semigroup, and beta is any other map from A to S. Then we can always define a map, say gamma, from A plus to S, such that gamma alpha composition gamma is equal to beta. Now here I is a map from A to S. So since A plus is the free semigroup, it's generated by A, so then by definition of pre semigroup A plus, there exists a map. It's actually a morphism here. There is a morphism. There's a morphism. Let's denote the psi from A plus to this S, because in our case we have a map from A to A plus, the embedding map, and here we have a map from A to S, which is the inclusion map. So then I can find a map psi from A plus to S, such that this diagram commutes. There exists a morphism psi from A plus to S, psi from A plus to S, such that this is here say alpha. So alpha, or you can say it's a phi. Okay, it's alpha, such that alpha composition psi is equal to the identity map. It is equal to the inclusion map. Okay. So this you can see this psi map. It's actually onto. This psi is onto here. Psi is onto. Psi is onto. So let's choose any element here. let x belongs to S. Let x belongs to S, then this x, let x belongs to, we need to show that this size onto. How do we do that? It's onto, its size a map from A plus, sorry, it's not in S. Let's choose any word here. Let say A1, A2, so on up to AN belongs to A plus, where these AIs, they are in A, because it is a free semigroup generated by A. Then by definition, A1, A2, 1 up to AN of psi, it's equal to A1I, A2I. See, by definition, you can see in the previous lecture, it's by definition. And but that A1I is equal to A1, A2, and here it is the product of elements of the A, treating A as a subset by A as a subset of S. It's equal to A1, A2 up to AN. So this is any element. Sorry. We need to put its onto. So that means we have to choose any element from S, and we have to find its inverse image in A plus, such that image of that element under size this element. Sorry, it's not correct. Okay, it's not correct. So to prove size onto, okay, size onto. Size a map from A plus to S. So let's choose any element in S. Let x belongs to S. Let x belongs to S. Now since A is generator, since A is generator of S, therefore x is equal to the product A1, A2 up to AN, where these AIs, they belong to A. Now I will find the psi image of this product. Because this product also lies in A plus actually, and that's equal to, you can see it's equal to A1I by definition, then A2I, A and I, where I is the inclusion map from A to S, and you can see this is equal to A1, A2 up to A, and that's equal to X. So treating now here this one A1, A2 up to A, and it's not the product of elements of S. It's just the word from the elements of A. So this element, this word, it's actually word here. A1, A2, so O, and is a word. In A plus. So it's not the product actually. So as like the product of the elements of semigroup S. But on this side, it's the product of the elements of S. So here it's a word, it's in A plus. So that means for any x in which is the product of elements of A and say n elements, there exists a word whose letters from A such that image of that word is equal to this product, which is equal to X. So that's size onto this. The size onto, it's onto map. So therefore, as we already proved, this S is isomorphic to A plus versus kernel of psi over kernel of psi. This psi is a map from A plus to S. It's ontomorphism, okay? Onto So by the fundamental theorem of homomorphism on semigroups, this S is isomorphic to A plus over kernel of psi. A plus over kernel of psi. So now every semigroup S has a generator. So whenever semigroup S has a generator, say A, then S is also isomorphic to some quotient of free semigroup whenever it has a generator. Since every semigroup has a generator, since every semigroup has a generator, so every subset of A appears to have this property, generator property, then S can itself be treated as a generator of S. So there is no harm in that. You can treat S as a generator of S also if every proper subset of S is not the generator of S, then S is itself a generator of S. So I can say every semigroup has a generator. So whenever a semigroup has a generator, then the semigroup is isomorphic to some quotient of free semigroup. Therefore every semigroup, every semigroup is isomorphic to some quotient, of free semigroup, is isomorphic to some quotient of free semigroup. Okay. Now suppose we have a finite generator for a given semigroup. So let's take if this A, the generator of a semigroup A1, A2, if it's a finite set, is finite, cardinality n, and if we can find a finite set, and if we can find a finite set, say R, which is actually a set of ordered pairs like W1 Z1, W2 Z2, Wn Zn. Okay, it's a finite set again, but these elements, this order pair, they belong to A plus cross A plus, where Zi comma Wi comma Zi belongs to A plus cross A plus. So they are the words actually, and Wi is a word, Zi is a word. So that means actually this R, it's a relation on, that's R is a relation, R is a, you can say it's a relation on A plus, because it is a subset of A plus cross A plus. Such that suppose this relation is suppose this relation has a following property, such that R sharp means the smallest congruence containing R, it's equal to, say it's equal to, suppose, kernel of psi. What is psi? It's already defined. Psi is on to map from A plus to S, and this S is isomorphic to A plus over kernel of psi. This is already done. Then we say that S is finitely presented, and it has a finite presentation, and it has a finite presentation like this. This S has this presentation A1. It is generated by these elements with the condition that satisfying these equations. W1 equal to Z1, W2 equal to Z2, so on up to Wn is equal to. This is the representation of the semigroup as generated by A1, A2 up to An. These are the conditions, these are the equations. So why it is? Because it is isomorphic to A plus over kernel of psi, and in this A plus over kernel of psi, this Z1 is W1 is equal to Z1, W2 is equal to, because they are related to each other. So that means actually this means the image, the psi of W1 psi is same as W2. Sorry, it's like this. Wi psi is equal to Zi psi for all I, because they are psi related to each other, as this R sharp is equal to kernel of psi. So they are psi related to each other, each pair. So in this quotient semigroup, you can say this W1 is same as Z1. Actually they are images, they are psi related to each other. But after isomorphic we can write it as like this. They are equal in S, because S is isomorphic to A plus over kernel of psi. And in A plus over kernel of psi, Z1 is same as W1 is same as Z1, W2 is same as Z2, and so on and so forth. So that this S is generated by A, it's okay, because A is a generator of, A is a finite set, it's the generator of S. But at the same time, we have a relation R on A plus such that this R sharp, the congruence generated by R, is equal to kernel of psi. So by the previous theorem, that already discussed in previous page, this S is isomorphic to A plus over kernel of psi, and in this A plus over kernel of psi, this is it's generated by these letters, these alphabets A1, A2, An, with the condition that W1 is equal to Z1, W2 is equal to Z2, and so on and so forth. Wn is equal to Zn. So in this semigroup they are equal actually. These words are equal. These words are equal because they are psi related to each other. So this is called the presentation of a semigroup S. So if it has a finite generator, then we can always present this semigroup. So now we have an example of finite monogenic semigroup. Let S be a finite monogenic semigroup. That is, our S is equal to M and R. What's this M and R? So this N is called the M. It's equal to. It's denoted by MMR. Okay, this M is called the index, and R is called the already defined this semigroup, finite monogenic semigroup. R is called the period. So what is this S actually? S is equal to, it's equal to like this, A square, so on up to A power M plus R. No, A power M plus R minus 1. This is our semigroup. And here A, it's this set. It is generated by the singleton set A. Okay, it's generated by this semigroup A. Now I want to find its presentation actually. It's generated by A. Okay, A is generated by A, but what is its presentation actually, under which condition? And you can see this, it's actually A power M is equal to A power M. That are the defining these equations for the presentation of this semigroup. Sorry, it's S here. S is generated by A with this condition: A power M is equal to A power M plus R. It's already discussed in finite monogenic semigroups. So this is S is actually it's equal to A with the condition that A power M is equal to A power, that's finite monogenic semigroup. Or we can also put we can define a relation. Let's define this relation R, in which you have only one pair, A power M plus R. Okay, A power m plus r. Okay. Then you can see this R sharp now psi is a map from A plus to S, and this psi of any element means A power it's say A power like n, which is equal to, but you can see it's psi of A, psi of A, psi up to n times, and that's again it's equal to A power n. You can easily verify this. This is the definition of mapping. So then in our case, because it's a finite monogenic semigroup, psi of A power m plus r is equal to A power m psi. So that means the pair A power m plus r, A power m, it belongs to kernel of psi. So therefore the R sharp, the smallest congruence generated by R, is subset of kernel of psi, because as this R is subset of kernel of psi. You can see it's trivial. R is subset of kernel of psi because this R, it contains this pair, and this pair is also in kernel of psi. So that means R is subset of kernel of psi, and R sharp is the smallest congruence containing R, and kernel of psi is also the congruence containing R. So R sharp is subset of kernel of psi. And on the other way, you can easily verify this kernel of psi is always it's also subset of R sharp. So that means they are equal actually. Kernel of psi is equal to R sharp. Kernel of psi is equal to R sharp. Then as previously discussed, as earlier we have discussed this this S is it is represented by, S is the following representation. It is generated by singleton semigroup such that what are the defining relation here? This R is A power m plus R, such that A power m is equal to A power m. This is the representation of finite monogenic semigroup. This is the representation of finite monogenic semigroup. And if the generator is a singleton set A, then the pre-semigroup generated by this set A is denoted by just A plus, not by the set A plus. It's just a letter A plus. Okay, that's the notation A plus. A plus is the semigroup generated by pre-semigroup generated by A. Now we take the example of monite.